Good morning, everyone. A warm welcome to the fourth session of Semiconductor Nation Campus Connect initiative, where we have this monthly series, which is also an initiative under Semicon India Future Skills by IESA. So under this initiative, under this series, we are going through the we'll intend to cover this entire journey from how it starts from sand to the electronic system. So as you can see from this slide that we'll cover one block at a time, and our intent is to give the students to give the students and the faculties how it starts from sand and how an electronic product is into our hands. So in the even the previous sessions, the session 1 to session 3, that are also available on ISA's YouTube page. And this session will also be recorded and will be archived, and you can go back and visit the session anytime you want. And also these sessions can be used by the faculties as a part of their lectures as and when suitable during the course during the course that courses. And also you are encouraged to put your questions or put your thoughts into the chat box, and we'll discuss those towards the end of this session. So now it brings me an immense pleasure to introduce you all to Mr. Pranav Kale, an expert in the semiconductor domain, and he's currently serving as the Senior Staff Engineer 2 at AlphaWave Semi. He has an experience of over 12 years into ASICs and SoC product development, and is complete owner of specification to silicon for HBM IP in ASICs and SoC. He is into logic design as well as firmware design for flash memory based USB mass storage class. Welcome, Mr. Pranav Kale. Over to you.
Hey, thanks, Sushma. Hello, everyone. Very good morning. Can start with the slide now.
Yeah. Just a second.
Yeah. So hello, everyone. Welcome to the Campus Connect session. I'm from AlphaWave Semi, as Sushma mentioned. Just about few words about my company here. We are a fabless semiconductor company with centers in multiple locations, including India. We have industry-leading SoC IP portfolio and complete end-to-end spec to silicon capabilities. Leading-edge IPs are completely developed out of India, including architecture all the way to the validation. For an example, HBM, LPDDR, or D2D. A previous session, as Sushma mentioned, we have gone through how IPs acts as a building block in any SoC. Today, we will be going a little deeper and talk about how to design digital part of that IP. Yeah. So what is IP actually? IP is a reusable, synthesizable logic block. It enables SoC ecosystem as pre-designed, proven IPs can be directly used so that for a SoC engineer, this gives more time to look after actual SoC level design challenges. For example, performance tuning, considering various data path in SoC. As SoC is a building block for overall ASIC and its main driver, all the tuning of all the digital logic path is very important to get the maximum out of that SoC. So for flow for presentation, we'll be going through broadly how IPs are classified as a first. Then core of this topic, that is various steps involved in designing of a digital part of this IP, what we call it as a soft IP. Yeah, next. Next slide, please. Next slide. Yeah, so slide shows here two cases which are well known to most of us. First case shows a clock getting displayed on our phone, while second case shows a high resource demanding app like a game is getting played. Both of these cases has their pros and cons on subsystem level or a system level. In case of clock, battery does not drain quickly. Also, there are no heating problems. While game case, we observe that our battery starts draining faster way than usual. Also, mobile starts hitting up a bit if you play for a while. Sometime there will be a performance lag that you will see even appealing in the visual form. Most of us are aware about what happens in background when we launch such apps, like how software functions or APIs get called by operating system, let it be Android or iOS or any of the mobile operating system, and what happens at the kernel level or how the firmware calls those API to get the services of the hardware. But I would like to focus on what must be happening at hardware level, which causes this power and temperature related phenomena. This example is taken because there are factors related to our current topic which can contribute to this. With this example, now we will start going into the digital IP design as a process. Slide. So broadly, IPs can be classified in two major categories, a soft IP and a hard IP. Soft IPs are IPs which are purely digital in nature. When I say digital, it is like designed using hardware description languages, are delivered in generally form of RTL code, and further steps in our project execution will take care of mapping or converting it into actual standard cells and implement. Hard IPs, these IPs can be purely in form of analog macros like PLL, the one which generates clock, or it could be a DLL, which is used to delay particular signal, or a IO, which most of us are aware of, input output, which takes care of input to and output driving to the external world and to the ASIC or chip. Or it can be combination of analog plus specially closed digital hardened blocks. Here, specially closed block means some modules, though in the form of RTL code, they are treated in a specific way and delivered in a form of physical block. So as shown in this figure, phi block is a combination of analog IPs like PLL, DLL, IO. PLL sits outside of that block. As a phi, it is a DLL and IOs, and some part which is digitally hardened block. So here that digitally hardened block is also made up of a standard cell logic. When we say standard cell logic, it is like someone wrote a code and designed that block in RTL form, but there was some special attention required while closing that block in the physical flow of closure, and hence delivered as a GDS or a hardened block to the external entity. While here controller and software are in purely in the form of hardware description languages that we use and delivered in the same way, that is RTL. So that next team will take it through the physical flow here. Now with this, we'll now go through how to design this soft part of the IP. Slide shows various steps involved here in the designing of the digital IP. First is specification study. That's where we start with. Then architecture, microarchitecture of that IP. Post that actual coding of the modules. QC check, that is nothing but a quality check. For example, lint, CDC, or synthesis. Final is the verification of that IP. It's very important block to check that the intent of the design is met as per expectation. Now we will deep dive into each of these steps, starting with the specification. Next. So IPs in general are targeted for some protocol. Let it be memory related, let it be networking related, let it be storage related. Specification study is the first step to study in detail protocol aspects of that IP and the targeted device. Say for example, here we have taken a case of a memory which ZX is the body as a standard body, which takes care of the specification overall. So that every memory vendor, every controller or a file vendor which talks to memory has to adhere and compliant to this specification. Of course, there will be some vendor specific changes, but in general, everyone will be compliant to this standard, which is set by ZX. Detailed study of this specification and keeping note of minute details is a key in defining the optimal IP. Few points which we should pay attention to are pin list. So understanding of what all input and output pins that enables access to memory. So in this case, since we are taking memory and that to be specific, here we are taking DRAM memory. Among that, all are the pins on which commands will get sent out. So if you study the spec in detail, there will be a different categories of commands and all. We'll go in some part of it. So we should, while in the specification study, we should see which commands will get sent out on the interface. What are the pins on which data will be sent? Which pins are used as a strobe or a clock pin to latch these commands and data bus? Which pins are used as a bidirectional pins? So this defines and this definition of the pin, it helps in the defining the internals of IP in a crisp way. Power up initialization. So how to power up and initialize this memory? Is there any requirement to follow some steps in particular or a strict order? Capturing these details is very important in the specification phase. As while debugging on actual chip, in case memory does not respond, issue could be as simple as not following proper initialization sequence. These are the initial steps that we should take care of while designing IP. Timing relationship, that is another important aspect. As shown in the diagram, note timing relationship across different signals. Based on this, overall performance of the IP will get impacted. Also, IP should take care of all the timings so that we do not violate the protocol. Interpretation of these waveforms and timing parameters is another important aspect. So what the way we say it, right? Reading between the lines and let's say a logical relation between various sections will help to understand protocol in detail. Since these are the specification, the way the language is and it's more technical, you may have to go through that specification multiple times so that you will get the gist of it. AC-DC timing parameter requirements. So AC-DC characteristics of the signal, their timing requirement in terms of timing that we call it as setup, hold, etc. These points are important in defining the operating frequency of the IP. Electrical specification is another factor that will help in defining our board or the PCB level parameters. We should be aware of the signaling or the voltage at which we talk to memory. Though as a digital part of it, it's not that important, but as a specification study, we should be cognizant about it. Then command and the state diagrams. So while designing, we should be aware of what are different commands supported by the given specification. What are the dependencies and sequences in which commands to be issued. So in this example, state engine of memory to understand which commands make memory to enter into particular state, how to make exit out of it. Go through this specification of the protocol multiple times. As we continue to study each time, we'll come up with more maturated decisions, which will help in overall design. So while designing or to kickstart with of the digital part of the IP design, we should be very well aware of what specification we are targeting, what are the limits of the design that we are targeting, what is the vendors available for any of the product you are targeting, and the detailed study of the ZX spec. Also, in case there are any vendor supplied data sheets or information, or it could be app note form. Let's go through it in details and capture every minute details of it. Now with this, we'll go to the next slide, which is architecture. Okay, so now we have understood, let's say, all protocol aspects of targeted IP. Next step is architecture definition. This includes overall outline of the IP, how IP looks like. In general, how, if I look it from the top view, how does it look like? What are the major building blocks of the IP? What are the different clock domains in the design? We'll go on this. Also, there is a separate slide for this. How is the reset structure? Of course, reset is our start point. Whenever you come up, reset will be gets first deasserted and your logic starts becoming live and active. So how your reset structure should be. So in architecture phase, we should be defining the details of this at high level, but we should start documenting all these aspects. How is the interface of the IP? So interface means how user should provide data to IP and in which form. Example, as shown in this diagram, we have divided IP in three major parts. First is control, or what we call it as a command path. That is all C0, C1 named modules. Those are mentioned here. That is modules in the upper path shows the control or command path. Middle layer shows the transmit data path, while lower layer shows receiver path of the data. Last block, that is named as a TX/RX, is the block which acts as a final interface module towards physical module. So as I mentioned, our focus is on the digital part of the IP. This TX/RX module will start talking to another block which comes so-called in the physical boundary of the design. So in this case, as an example, let's say whenever user issues a write command for a data to be written in memory. So let's say user want to write at address 0 with some data, and that request arrives at our input of the IP. Of course, we have designed how user will provide that data, how that interface will look like. So user has initiated now this. So how the flow of the commands will be. So flow will be upper path will follow all command requirements since it's a control and command path, and sequence as per the memory specification. Say sending command, it could be like sending command A, then sending command B, and then finally actual write command with targeted address. Because in the specification, it may not be like just write to address X. There could be prerequisites and the postrequisites to that command. So that upper path in this architecture phase and in this diagram will follow that all those aspects of the command sequencing. At the same time, middle path, since we want to write data, middle path will come into picture, will process incoming data and sends that data over following, considering all the timing relations between write command and data as mentioned in the spec. So that waveform study will help here because we know that after sending write command, how a data should arrive after how much time, all those details since we have retrieved from the specification study. In this architecture also, we should think of whether we are really following that aspect. Is the timing requirement met? So that we'll end up designing our blocks accordingly. So just to give a real-time example, in one of our ASIC project, we found one issue, which is major block in the major block of the design. Since it was ASIC, unlike FPGA, we can't resynthesis and generate a bit stream and give a rerun. So all logic is frozen now and we have a chip in hand. But fortunately, architecture was defined in such a way that we could directly access output interface of a buggy module that we have identified, but from external world. So we did fix that buggy module, of course, added it in FPGA. We're able to do synthesis of it, generated bit stream, and then eventually bypass that buggy module within the ASIC. So this way, defining architecture in a flexible way and considering all aspects with maximum possible cases is very important so that we will have a workaround in case we're stuck somewhere. With this, we'll move to next slide. Just one previous. Yeah, so as I mentioned last time, there could be a multiple clock domain case here. So in general, IPs nowadays are very complex. It could have a single to multiple clock domains. So for example, as everyone are aware of, there could be a CPU or GPU working at different clock than peripheral or other IPs. As shown in this example, block that drives data to this IP is operating at, let's say, 500 megahertz clock, while all modules within the IP are working at 1 gigahertz. So data entry and exit out of the IP towards user side is all at 500 megahertz, as shown in this violet purple curl, while IP on itself, since it shows same color coding, is whole operating at 1 gigahertz. So here, input and this output data stage module, which converts this 500 megahertz clock domain data path signals into 1 gigahertz clock domain and vice versa. So that module will take care of this handling of a signal traversing from one clock domain to other. Also, it does include like special logic which transfers from slow speed, that is 500 to 1 gig, and other way around also, because these are different techniques used in the different clock domain crossing cases, fast to slow or slow to fast. So there are special techniques which will be used here. We'll move to the next slide, which is microarchitecture related. So next step as a part of architecture definition is micro level definition, or what we call it as a microarchitecture of building blocks of that IP. Just like our SOC case, we went inside that IP, how to define that IP. Now inside that IP, we define the architecture of overall of that IP. Now we'll go into the within that IP, within that architecture, how to define the internals of every block of that IP. So in this step, we should define how different modules in IP communicate with each other. Just like what we defined, how IP will communicate with user logic, even within that IP, how every module will communicate with each other, defining latency optimized interfaces for such communication. So when we say latency optimized, meaning the communication between two modules within the same IP should be as fast as possible. When we say fast, it is in both, like in terms of frequency, also in terms of how many clock cycles it takes to transfer a signal from one module to the other module. The details of internals of every block we have defined in this step, including the finite state machines. There could be a combinational logic. All those details should be get defined properly in this microarchitecture phase. Another aspect, just like what we studied in the specification study, that is the timing aspect, how are the signal timing relationship, even in this case, within those modules, how are the input and output timing diagrams for every module, how they will look like. We have to document all this, think over it in this microarchitecture phase. Another important aspect is debug hooks and support for testing of the logic. Like for example, self-data generators and checkers to test given block without external inputs so that you can test your IP independently. Programmable support for some of the parameters. This is very important. This gives you flexibility to handle challenges once design is frozen. So unlike FPGA, as I mentioned, in case of, let's say, IP targeted for ASIC, once our design gets frozen, it goes into the physical implementation phase, and then you are not allowed to change of the any code or the RTL. Of course, there are other bypass methods, but those has the limitations. So example, in one of our ASIC project, what we did is there were factors which changed a lot post design phase. So fortunately, IP was designed in such a way that those factors are taken under programmable support. So how this helped? This helped with when the chip we were bringing up, we were able to operate it without any issue because our specification or the targeted, let's say, a vendor change or the target operating frequency change. But fortunately, IP was of course timing closed on those frequencies, and soft part of the IP was also supporting some of the features under programmable support. So we could make it as a workaround, or it was working well. So programmable support is, when we say programmable, it is something like which hardware designer defines what happens when software or someone writes particular bit or support for parameters which can change over time. So in this slide, one of the example for one of the block that we discuss in the architecture phase is shown. Here we have defined internal details of one of the module. So how data gets stored in that module, how write and read pointer gets implemented, and based on the pointer values, how data gets stored in particular location and how you can fetch that data from that module. So these are the minor details, like if possible, you should go till the as low as possible. Let it be mux implementation, let it be any and or logical combination gate implementation, define all aspects of it. You can analyze the latency of that module also. This overall helps in a very less or bug-free design when you really code. Otherwise, your design will be very patchy in work. So we'll go to next slide. So as I mentioned, debug is another important aspect of overall soft IP, or it could be any IP in the overall chip design process. As part of soft, we should have enough hooks or visibility within IP for debugging issues on actual chip. It can be self-logging as we discussed, like data generators, checkers, so that we can check that particular module is really working well or not. As shown in this diagram, we may have a logic to monitor clock generated from chip. So there is a PLL or there is any clock generator in case you don't get expected responses from IP. Of course, to start with is check whether a clock is there or not. So based on, let's say, external button as shown here, button, if you press that button, there will be a clock divider in the logic that you might have designed, which will output particular clock on the GPIO. And then over that GPIO, you can connect any of the digital or analog oscilloscope and observe that waveform. So this will help in debugging whether, let's say, your PLL or clock generator is operating well or not. In some cases, even since you are able to observe that clock, it will help in analyzing the quality of that clock generated. Some signals can be result of big procedure completion. For example, when we, let's say, a boot, or when we initialize our IP, or when we do power up and initialization. Such signals you can brought it out on LED as those are visually appealing, and you can see that, oh, now IP is up. Now IP must be ready for taking our data or the commands from the upper layer logics, or it could be, for example, CPU. Now my IP can receive a data from CPU and we are ready to write or read from memory. Some are interrupt signals, which you can brought it out on GPIO, because for an example, in your ASIC, let's say, this interrupt is eventually connected to a FPGA sitting on the board. So whenever some procedure is there, there is some interruption via GPIO, FPGA will get notified and then corrective action or the reaction to it will happen. So unlike FPGA, in case of ASICs, there are limitations while debugging. So whenever you design IP, this is important aspect to consider. So well thought through debug hooks are very important. We can insert advanced debug structures also. But remember, there should be a balance between actual logic and logic helping for debug, because this is unfortunately finally a debug logic. So you should be aware of how much logic you are inserting for debug. The actual intent is not debug. Actual intent is, of course, to work with that given protocol. Now, next step, we'll go for the RTL coding. So here onwards, the actual coding starts, or the actual implementation of the design starts in this step. Coding can be using any of the hardware description languages like Verilog, VHDL. Even there are nowadays tools that are smart enough to take other languages, abstract languages like C also. Like any other language coding guidelines, we should follow proper indentation, comments, so that code becomes more and more readable. Even another engineer works on it, another student works on it. It should be handy enough to take care of it in future. In case of Verilog, there are parameters and defines which you can make use of while coding, and it can help you to make your RTL or the C Verilog code in more and more generic form. So this helps in expansion of a design, just playing with some of the parameters or define. For example, your earlier input interface or the input data stream presented at the IP, let's say, has a requirement of 256-bit data bus. Now there is a change and you have to implement or start supporting 512-bit of data bus. Now, if your RTL code is such a way that you have used enough of the parameters, then when just by changing that parameter at top of the module, your IP can start accepting or responding over that 512-bit bus. Of course, there could be some logic areas where, because of the 512-bit of nature, we have to add some custom logic. As we discussed, there could be a way of defining it under certain defines. So the combination of this parameter and define can help you in such a way that your 80% of the RTL code is remaining same. Only 20% of that code is changing just because we have to now start supporting 512-bit. For example, let's say our whole control path in the above example will remain same, but while our TX and response data path, just by changing parameters and some defines, start supporting another bits of the bus also. So while RTL coding specifically, few other points that we should be take care of are appropriate assertions. It reduces your debug time to great extent. So for example, value of certain variables in design is not as per expectation. So assertions can catch such issues instead of checking and going through waveforms and identifying this issue. Because let's say some of the parameters or some of the programmable support you are supposed to configure with value 3, maybe the testing logic ended up configuring 4, and overall simulation is failing. Debugging it and going it through waveform from all the modules will be very time consuming process. So being more productive here, we can make use of assertions here, and that assertion just can show it in your log and oh, that's the issue. Just change it and we can move forward. Cover properties in RTL or Verilog code or VHDL code helps to achieve faster coverage closure. Coverage, we will talk about it in subsequent slides. So with this, let's say we have done with the coding part of the module. Now we'll go for the next step, which is QC check. So now coding is complete. QC check, that is nothing but a quality check of this whole design. So it starts with, let's say, a lint. So this is a check where all coding guidelines, whether your design is synthesizable or not, is there anything which is will fail when you really implement it in a physical flow. For an example, it's a latch getting inferred, or there could be a basic issue like single wire or a single flop output is getting driven by multiple logic. Of course, these multiple drivers are not acceptable. So those warnings you will see it when you run a lint check on it. So we should fix all those critical warnings or errors, if any. This help is not only in terms of synthesis, but also for the verification, it will be of a great help. So lint check is the first step. CDC, as we discussed, we may have multiple clock domain designs. So in this step, we can check for design violations of signals crossing from different clock domains. So as a pictorial view, I just showed a signal traveling from very slow clock domain, reaching from a source to the destination. And the destination is really fast clock domain. But there was a, let's say, for example, a signal that we pointed here is transiting from a slow to fast. And there was not enough care that we took here while designing. So in this CDC check, what will happen is that signal will get catch and we can fix those issues because the tool will report that, oh, this signal is violating the protocol or the timing aspect of the design. So this check is very important. Synthesis. So finally, what is the intent? The intent of our design is to infer hardware, appropriate hardware out of it. So this step itself is a big process in overall chip design and is an entry gate to the physical design or physical implementation. However, for a digital IP, this is also important. We can use it as a flow flush for our basic synthesis. So our IP should meet targeted frequency of operation. This initial synthesis will help to understand timing of the design. In case there are timing violations, we can redesign some part of the logic, optimize it, or add pipelining to fix these timing issues. So here pipelining means we may have, let's say, a big logic path with a flop, and the output of that flop goes to big combination logic and then reaches the destination flop. Now this combination logic was such that it starts violating your setup hold requirement of a destination flop. Then we can add another stage of a flop in between, which is called as a pipeline, and we can break that path here. So though as a part of soft IP, but we should do synthesis, and as a check, it will give you a early indicators in case there are violations. Another aspect is area. So IP is a hardware. It's not like any of the other code. It will consume resources, and hence area should be as small as possible. IP operating at a 1 gigahertz with, let's say, a 4000 gates is of course preferred than similar IP with the same functionality, achieving all the functional aspect operating at 1 gigahertz, but starts consuming 600 thousands of a gate. So this is very important. This will go to next slide. So verification is another aspect of digital design flow itself, because without this, our design is not complete. Intent is to verify design works well and as per the expectation that we are targeting for with the targeted functionality. So the block or the infrastructure, what we call it as a test bench, used to verify this design can be simple or very complex. The IPs are also becoming complex, hence this verification flow are also becoming more and more complex. So as shown in this figure, inputs of the DUT that is nothing but design under test, or let's say here A, B, and a clock of that flop, input flop, while outputs are Y and intermediate flop output, which is not visible to external world, but it is present, which is Q. So here this driver block drives all possible permutations and combinations of A, B, and this clock signal. So while monitor and scoreboards checks for the output of the design against expected or our reference value. Comparison logic present in the scoreboard will fail if design output Y does not match with the expected output of a given combination of a design inputs. So here we'll check for A, B, and clock. Let's say hypothetically 2 raised to 3, 8 combinations possible. Any other combinations also. For example, clock stop. For all those combinations, what is the expected output? So that automatic checker will check that. And with less time, you can cover all the possible combinations. And in case there are any issues, bugs, we can fix them. Coverage closure, as I mentioned last time in previous slide, it is another important aspect. Coverage closure ensures all targeted functional requirements are verified and getting covered properly. Code coverage is another aspect while designers should consider while coding. As discussed, along with assertions, we can add those cover properties while coding. So code coverage analysis will ensure all logical path within the designs are getting verified. Let's say you have a big FSM, lot of case statements. So in code coverage, whenever verification tool dumps out the coverage database, we can analyze that. And in terms of code coverage, from digital part of the design, we can concentrate on, let's say some of the FSM transitions are not happening. There could be two reasons. It could be false transitions, or it could be over design, or it could be a miss in the inputs of that IP while driving from the driver or the verification aspect. Like these are the inputs which should get driven, those are not getting driven properly. So all those misses or catch we can do while analyzing code coverage of our design. So this is another important aspect. Next slide. So finally, your IP should get integrated somewhere that we design for should be in a form that it is easily integrated in higher logic layers. So there should be minimum overhead of logic design while integrating these IPs. So use of basic cases, let's say use of standard protocols like AXI, APB for configuration, or any other industry standard which will help during integration. Or it could be all custom, but then that custom has to be delivered or inspect out to every team member so that they will end up their designing IP in such a way that they are compliant to that custom interface. So as shown in this diagram, we are integrating multiple IPs here. Let's say a DRAM block, DRAM IP, SPI flash controller, or it could be encryption engine and CPU eventually controlling all of this. And there is a intermediate bridge block or interface block in between, which acts as a mediator across different IPs. So while design of IP, let's say if DRAM controller IP design and SPI flash controller IP design has followed all the standard procedures and their interfaces are also standard interfaces. Of course, they are compliant to the bridge interface. Then someone picks this up while integrating it at SOC level, it will be very easy. It will be like plug and play like case. Of course, there will be some customization, some special care required, but 90 to 95% interface is compliant. So that will be very handy. But let's say an encryption engine case. It has its own interface, which of course is suitable and optimal for that block as such. But that interface is very custom. It is defined in its own way. So it can't communicate with this other three of the blocks or this bridge which acts as a mediator. So what can be done here? We have to then write one wrapper out on top of it, write some glue logic, which let's say converts a bridge interface to this custom encryption engine requirement interface and vice versa. And then by this, we'll make it compliant to the bridge interface and then overall system will work well. So this is how you can handle standard interfaces. If your IP is compliant to that, that is very good. If not, then you can take care of it by adding some extra logic on top of it. Slide. So we'll now come to the summary part of our presentation. So in summary, while designing IP, we should be keep these four aspects in general in mind. So power, the battery symbol, everyone is aware of. Performance, area, and generic or flexible designs. So way we architect all the way from architecture, way we architect our IP, the way we code, coding style, all these aspects also contribute to power. It's not like only the architecture part. The way you code in RTL, improper coding will also end up consuming a power hungry and making the chip more and more power hungry because of the way you code it. Less power and area with the highest performance is the aim. IP should meet, of course, the targeted frequency of operation at specific conditions also. Here conditions means targeted temperature and voltages. Remember that mobile example that we took, the behavior of that mobile during clock and game case. So in case when you're playing some HD kind of a game, it's a combination of performance and power consumed, which shows in the form of heat and battery drain. While in case of clock, just clock getting displayed, since its hardware resources at that time are not that demanding in terms of performance, it shows its impact in battery or mobile temperature accordingly. Of course, this is one of the factors for in that example. There are other system factors also that contribute to those phenomena, but hardware point of view, this is where one of the bigger factor is. Protocols are becoming more and more complex and high speed. So if we compare last few decades and this, frequency and the complexity or requirement of hardware is growing at lightning speed. So IPs that we design should be generic enough to sustain this requirement. For any change in the protocol, it should be incremental change to the design, at least that is the soft part of the design at least on digital front, so that IPs can be easily scaled as per the ongoing demand. Slide. So finally, let it be any design, let it be digital, analog, or physical form of a design. Teamwork is a critical aspect. Everyone is aware of it. Now, if you look at the IPs in current age, they are not only digital or only analog in nature. They are a combination of multiple things and becoming more and more complex and even big in the sizes. IP design includes a cross-functional team engagements like analog, digital, physical design team collaborating and working with each other. So for successful designs, defining and following processes during the handoff or deliverables from one team to another team is very important. So just to give you background here, in one of our project, we faced an issue. A memory was not responding at all because that IP was targeted for memory. Post some debugs, we found that a very basic issue, but it's important. We found that polarity of one of the signal that was connected to IP from a PCB or let's say a board, it could be a push button, it could be a jumper. It was a inverted in nature. We were expecting a logical high value, but when you connect high, it was giving inverted version of it that is low. So it's not only about ASIC or IP design, but all the way up to final product, including PCB board. All these is a teamwork. Working on design on actual silicon with our targeted specification is finally our aim or ultimate goal. Any bug that we identify on actual chip is very costly affair and has a big turnaround time. So for example, let's say there is a bug in a software. There is a way we can make another software patch or a software update like the way we received it over apps. But what will happen if there is a bug which is very critical and in that is there in ASIC, of course not in FPGA cases, then that is there in the ASIC. So you can imagine the procedure and the turnaround time involved here of fixing of that bug and getting your new chip back. It's a huge time. So verification, design, physical part, every aspect, it's all teamwork. So that is very important. Yeah, next slide. So with this, I'll end my presentation here. Thank you all for the participation. Let me know if there are any queries. Handing over to Sushma.
Thank you, Pranav. Thank you so much for giving us and giving our viewers such a nice understanding about the IPs for digital design. So maybe we'll start with some round of discussion after the the beautiful session which we have shared with all of us, and that which the viewers can watch even after the sessions are closed. So just to start with, to give the students, to help them gear up when once they are coming up into this domain, when they are trying to enter into this domain, that in your experience, what are the biggest challenges that they could face or that currently you people are facing in creating an efficient digital IP design?
Yeah, so major aspect that we see in general is whenever we do, let's say, projects in B or our last year, the availability of the hardware resources or the hardware that you choose. So while making those projects, you should be aware of what is the hardware available in our own college, what are in our own lab. So for IPs that you are targeting, let it be a very basic IP. But if you go through all the flow and implement it very properly, you will get nice exposure and experience. So the challenge that we face while in the industry, people or students will go through the big IPs, but since those are not inferred any of the hardware, the exposure or the minor concepts which are very important, those were missing. So I would recommend you should go actual on the hardware, not just limit yourself to the simulations.
Okay, thank you, like for giving our viewers a heads up on how they should start, what thing they should point out to start with, maybe in their second year or third year, or maybe in their final year.
It may not be a complex boards, but whatever is available, try to go over the hardware.
So that's a good suggestion. That what facilities are available. Let's
Yes.
first start building the things around that, and then we should focus on something which we can get over the period of time. So we have a question from Mr. Ashok Kumar. So he had what does clock domain crossing means? Maybe like if you want, I can float that slide, or if you.
Yeah, yeah. So yeah, you can float that slide, Sushma. So that's the reason I use that very simple pictorial presentation here. So you know that there is a frog here, and that frog, of course, is slower than that rabbit shown. Of course, this is a very simple example, but just to understand this concept is one. I am speaking in one language with one pace, while the receiver is in another understands another language and another speed or the pace. So here that signal should travel from that slow speed domain uh, and reach the destination domain, which is very fast. So for example, speaking in the technical terms, the signal was launched in a 1 gigahertz clock domain. So a clock period is of 1 gigahertz. So a pulse that we want to transfer from this 1 gigahertz domain, but the receiver is operating at 500 megahertz, or it could be in terms of 100 megahertz. So there is a high chance that those edges are not aligned and you will miss that pulse because the width of that pulse was in terms of 1 gigahertz domain. So what could be a technique here? You have to extend this pulse so that it gets properly recognized in the 500 megahertz domain. So this is one of the case where you can do a, let's say, a pulse stretching and so that it reaches. So clock domain crossing in ultimate is a concept is crossing of one signal which is from a different frequency which may not be synchronous. When we say synchronous, source may not be common, their clock relations may not be common, but we want to capture it in particularly totally asynchronous domain. Just to give real time example, when you press a push button or a power button on your mobile, it is a human interference where the clock relation of the internal of the mobile is completely unknown. It acts as purely asynchronous signal. So those signals which are doesn't have any relation across the two departments or the two compartments in your design.
Thank you for giving a quick, I'll say, quick liners about clock domain crossing. He has another question. Uh, like just a second. Yeah, RTL file is only one file, or it can be multiple.
Oh, no, no. So you might be aware of how it happens in C, right? Let's say I wrote a function in one of the file. Then I wrote a different routine for initialization, or it could be a boot initialization in another file. So you might see, as let's say, if you see operating system, you will see, or any of the app, you will see thousands of file contributing and making that app. RTL is also similar way. So as you see, saw that in that architecture, we were having, let's say, 4 blocks in our TX, 5 blocks in our middle data path, 1 block in the response data path. Those are representation. But when you really micro-architect it and code it, the response data path, though shown as 1 block, it doesn't mean it is a single module or single RTL file. Internally, it can have 5 or 10s of the files. That all depends on the way we structure our code. Of course, it's not a single file.
Thank you. So, like, there's another question. So, in the previous session, the viewers watched, or they like, if in the future when they are watching this series, they'll go about analog IP. Today, we have talked about digital IP. So, maybe like to give the students some few liners, like what are the key differences between two IPs, because they'll see, okay, I have watched analog, I have watched digital IP session. So, because they go through the, like I'll say, they go through a chapter, but still sometimes they have that confusion,
Yeah. Yeah.
like
So
what is this and what is this, like if I'm comparing the two.
right, right. So let's say if you take PLL or a DLL as a block. So DLL is nothing but, let's say, a block which the signal arrives at the input, some delay we want to introduce on that signal and then reaches output. Now this we call it as a purely analog block. When we say analog, finally everything is eventually getting converted to hardware, let it be any of the fab. But why we are separating it out, because analog will have its own challenges, since the PLL will have its own requirement of uh, jitter or a duty cycle. So the design will get defined in very minor details, including the transistor to be used, PMOS, NMOS, their characteristics, all those details. When we say digital, we are talking in little abstract layer. We are talking in terms of code form. We are not inferring direct hardware. If you look at the netlist or the hardware inference of it, it will be in terms of a flop. But in analog, what happens inside that flop is also important. And nowadays, analog is also big thing because it is more and more complex. It includes big designs also. But with digital, you can, so SOC, of course, you have to design and integrate in digital form because of the size or the nature of that hardware. Analog is details and more performance and minor details of a given block. But when we say given block, it's more generally targeted towards the external peripherals, or that one signal in terms of electrical talks to the external world in general.
So thank you. So sometimes, because like as a student, sometimes we go through it, but then we are confused at what's the exact difference. So thank you for giving these pointers to them, that okay, these are the basic difference that analog and digital IP have. So uh, there is another. No. Maybe we can have one last question. Like in this rapidly evolving technological landscape for this entire ESDM thing, maybe in other domain, like it's happening every day. The things are changing like anything. So, what are your suggestions for our viewers to stay updated with the latest trends and advancements that are happening into, say, precisely into the digital IP design? I mean, how?
Yeah, of course, all of this reading available on any of our social media, not social media in terms of, but like knowledge-based media, and going through real specification bodies like ZA, or it could be IEEE membership. Going through all those, you will be on top of, or on the cutting edge of the node. Maybe some of them are very specific and very focused on particular block, but you will get at least the gist of it. Also, the other sites which generally talks on about electronic happenings, you can follow those slides. You will get the most details.
Okay, thank you. So we got one more question.
Yeah.
It's by Mr. Ashok only. So, what is a pipeline, and can it be used to take the to capture the data in the next cycle?
Of course. So when we say pipeline, that word as such means adding, let's say, adding a flop stage. There are multiple ways to close your timing path. So as I explained during the presentation, let's say a flop launching and the destination flop has a big combination logic. Let's take a real example. Let's say those are operating at 1 gigahertz, which means 1 nanosecond of a period. In between, the combination logic itself is taking 1.2 nanosecond of time, that is 1200 picoseconds. Of course, you may not reach that or meet that path, because the time that signal reaches, you may end up violating setup, hold, or the functional aspect of it. So when we say pipelining, what is happening is we are adding a stage in between and breaking that logical path in two forms. That is, first, some part of the processing will happen in the first clock, while second will happen in the second clock. For example, let's say I want to count all the ones present in my 1K of a bus. So it will be a 1 bit adder for 1K times. Now, if you look at that adder circuit, it will be a big circuit. It may not meet your timing. What could be another way? Let's break it in two paths. First, let's calculate it 512 bit, consume one clock cycle there. Go to the next cycle, use the previous data and the current 512 bit, and then compute your logic. Your design latency is increasing, but you will be end up closing it well. So pipelining in general is way to break that path. It could be a flop addition.
Thank you, Pranav. So we got one more question. So it's from Brahmendra. He's a student from SRKR Engineering College, which is in Andhra Pradesh. So his question is, what open sources you would suggest for students to do projects, as many of these facilities are not available with many of them. So
Yeah,
what
there
are
are,
the solutions on the open sources?
as I mentioned, as a exposure, of course, better or preferred ways to go over hardware. But you can Google it or you can search online. There are simulators which can help you to simulate your Verilog code also. But since real learning is with the hardware, if possible, even though your um, resources are not available, there are some basic boards also which you can order online and test your code on that. There are trial versions of some of the tools via which you can do the physical or synthesis part of it, specifically on the FPGA front. And within less resources also, you can go on real hardware. But there are online tools which will help you to for a simulation purpose at least.
Thank you. So I think now we are getting more questions. Maybe we can just take this one. So
Yeah.
Pratik Agnihotri is asking and uh, which tool and Linux, how do, I think the question is not formulated properly. So I think the question may he intends to ask that which tools should they go for use for physical design, DFT, GetNet list for SOC.
Yeah,
If
so each keyword here itself is a big topic. I'm sure it will cover its own. And there are dedicated and well advanced, well proven established tool sets. I won't name any of them here, but there are tools from big aspects here and a big establishment which you can use very easily and implement it in physical or DFT or any of the test logic or physical part of it.
okay, so maybe I think now we don't have, yeah. So then we'll close this session. Thank you so much, Pranav, for interacting with our viewers, for sharing this the thought, the information and intellect which you have gained over the period of time with them, and for sharing your experiences with them, and also for giving them some pointers that how should they start preparing if they are interested into this domain. So thank you so much for being a part of this webinar series, and we'll look forward to having much more interactions with you in the future.
Sure, Sushma. Thanks a lot. And this is a really great initiative from IESA also, College Connect, because with this we'll get chance to interact with the students. And also, it will benefit us because we'll get very good students and they'll start really working on real hardware in semiconductor world. Thank you.
Thank you. And thank you, everyone. Thank you to all our viewers. And also thank you to the viewers who will be watching it in future. So thank you so much for joining us, and for also to visit this webinar series over the period of